Okay, let's look at this problem. This is like a 20% problem of the exam. The previous one, the centroid x bar and y bar, was 5%. So let's try to gain as much percentage from the points that's given in the exam. This is a very simple problem, but I need to know if you could get like a full mark in this type of questions. You can see here, this is the fixed support. It's not a hinge, it's not a ruler. So there is a reaction. You can see it's given. The reaction. Let me turn off this. So there is a reaction. AY, which is 30 kilonewton. And you have a moment, and this moment is, let me just erase this. The moment is counterclockwise, 216 kilonewton meter. 216, yes. Okay, and now you need to determine draw the shear moment diagram and find the Vx, Mx for the only for the member AB. Let's do the simplest one. Drawing a shear diagram is very simple. You just like extend the lines where you have change in loading. You always have to put that this is the shear. You have to put shear V, and you have to put the unit kilonewton. And that is, you can see it here, kilonewton, kilonewton, kilonewton. Okay, you start from 0. And you can see here that you're going to go up 30 kilonewton up at that point. So you're going to go 30. Of course, you don't have to put kilonewton because you have the description of the axis here. From that point, you don't have to worry about the moment because right now we are drawing only the shear diagram, not the moment diagram. And it is not constant because look at this. There is a uniform loading, and this uniform loading is 2 kilonewton per meter times 6. 2 times 6, it is 12. And this 12 is down, and it is 12 kilonewton. So, from here to here, it is 30 minus 12. 30 minus 12, if you do it by 2, this is 8, so it's 18. So it's still plus. Let me erase this. 30, and here it will be 18. And since the load is uniform, the shear would be linear. So it's going to be linear. So this is linear shear. It's not linear, it's not curved, it's linear. And you could notice at point B that there is also a point load down. At point B, there's a point load down, 10. So 18 minus 10, you're going to go down 18 minus 10, and that is 8. So you're going to go down at this point. Oh. And this is 8. You can see from B to C, there is no loading. So the 8 would be constant, uniform, all the way until you come to this point, and that is 8. And at this point, point C, there is an 8 down. So 8 minus 8, that's a good check. So this is going to go back to 0. you can see that the shear here is plus and the shear here is plus. Now, how could we draw the moment? Let me erase this. Let me erase this to show you. So let's draw a moment diagram. Moment, and you know the unit for the moment is kilonewton dot meter. We should start from point A. I know some students, they start from C, from the other side. Whatever way you like. I like it to go from left to right, and this is what I was trained, and this is where I think all the books show how to do the moment and shear diagram from left to right. So you can see that at point A, there is a moment. And this moment, remember from the moment sign convention, if it is counterclockwise, it is a negative moment. Okay? So this is a negative moment. This is a negative moment in the moment sign convention because it is counterclockwise. So you're going to go down at that point, down to 16. And of course, that down is negative. Okay. Now, let's look. There's no other moment from A to B. There's only loading. So let's find out the area of this load, shear. There is triangle and there is rectangular. And if this is 18, so what is, again, what is 30 minus 18? 12. So this is this is 12. So 1/2 times 12 times 6. So 1/2 times 12 times 6. So 6 times 6, that's 36. And this is in the plus. And let's find the other area of the shear. It is, you could notice, it is 18 times 6. Let's find out 18 times 6 is equivalent to what? 18 times 6, and that is 108. So 108 plus 36. That is 144. So from here it is, from this point it's minus 216. To point P, there's no other moment. To point P, to this point, it is minus 216 plus 144. So let's look at this. It is 2. You take 1. It is 11, 7. And this is minus 72. So from here to here. And you can see that this is linear. So eventually it is nonlinear. So it's going to go from minus 216. Let's just do it. This is not to our scale. So minus 216 to that point. It is nonlinear because of this linear shear. So it's nonlinear, and it goes to minus 72. Okay, just put it to get the full grade. It's a curve, concave down, nonlinear, whatever description of this curve is. Now, you can see that this shear here is uniform, so the moment will be linear. So let's look at the area. This is 8. 8 times 4, 32. So minus 72 plus 32. This is 0. And this is, so it's minus 40. But remember, that's going to be minus 72 plus 40. It's going to be linear. This is going to be linear still. So it's going to be linear. And the answer here, it is minus 40. Look at the moment, all negative. And this is linear. Let's look at the moment at here. Look at that. This is clockwise. So clockwise moment in the moment sign convention, it is plus. So plus 40 and minus 40, back to 0. This is a nice check. This is a nice check. So we draw the shear diagram, we draw the moment diagram, and now let's find out, he need only the equation for the segment